seeing blank stares. You're not watching enough war films.
I know what you're talking about.
All right, thank you. One of you.
What is it?
Sten gun?
I don't know.
It's a machine gun
Like
whose
rapid
magazine
fire.
goes in this way. Right?
Oh, yeah.
This way.
Oh,
Okay,
okay.
All right, so
not a good person.
Sten gun.
Sten gun.
All right, the bullets come out that way. So your finger points in the direction that the positive particle's going. Boom.
Boom.
The multiple fingers here, the magazine cartridge, well, magnetic field is never just a single thing. You've got a magnetic field, you got a whole bunch of them, so these fingers go in the direction of the magnetic field. The thumb points in the direction of the force. The trigger is the thing, this is the hammer, that's the thing that basically forces everything to happen when in a gun. And yes, it's just a memory trick for you purists out there. Stick guns don't really work this way. But this is another right hand rule. So I got positive particle going that way, I'm pointing in that direction, magnetic field, my multiple fingers pointing outwards, thumb points up.
It's the same trick, you just leave your pointer finger out instead of curling it in.
Yeah.
I like this better.
All right?
So happy for you.
I like this better. Because I always have a hard time where I do my insertion, my initial
The like
Okay.
curling.
hand
yeah,
insertion.
I
Yeah.
think of it like with torque, and I'm always like, do I go this way? Do I go this way? Yeah.
Yeah. I like the Sten gun.
All right,
Alternatively,
then we're gonna,
not.
now, just to make matters more confusing, see, the Sten gun is the one that I remembered. The textbook does a slightly different right-hand rule for it. So with a palm, and you force it, but yeah, I know it, it's just not one that pops in my head first. So when this proton enters that magnetic field, it's going to get forced upwards. So now it's moving in that direction. In which direction will it be forced?
Is it in that direction?
Pardon?
In that direction?
The direction it's moving? No. Because the force is always going to be perpendicular to the direction of movement and the magnetic field.
Wait, what was? I'm sorry.
I'm
can you repeat
confused
the
about-
question? I thought
Alright.
you just asked the same question twice.
Yeah.
So when the proton enters the magnetic field, it's forced upwards. But then it starts moving upwards. So let's say at this point right here, which way will the proton be forced? Its velocity has changed direction, so the force will change direction.
Okay. So now it's going this way.
So now we're doing J hat cross K hat.
So it's gonna go back down, like to the negative I hat direction.
No.
Positive I
All right.
hat. Right?
All right, we are dealing with components here. Conceptually, there's a much simpler way of looking at it, but, so, let's take the extreme of, if the proton's moving this way, which way will it be forced?
Positive I hat.
Yeah, all right, so that'll be forced in that direction. When it enters like this, it's forced in that direction.
Curling.
When it's partway in between, which way will it be forced?
Between those two?
So then fingers would go this way, but they're curling this way. So it'd be, yeah,
Yeah.
okay.
Or Sten gun.
Sten gun.
Now,
I should have just done my Sten gun and I would have had it before all of you.
recognize that this force is perpendicular to the velocity. No matter what the direction of the velocity is, that force is always perpendicular to it. Huh, where have we seen that before?
Work.
Oh,
Not that chapter.
yes.
The force that's perpendicular to movement.
Centrifugal force?
Say it again?
Centrifugal force?
It sounded like you merged the two words.
That's possible.
It could be that I just misheard. Centripetal?
Not centrifugal, but yeah, centrifugal.
Oh, yeah, not that one. Centripetal, centripetal. That's a centripetal force in this situation. So we can take it one step further. The velocity and magnetic field are perpendicular to each other, so the cross product is at the maximum. Just Another quick review here, that force, the magnitude of that force is equal to QVB sine of theta. If theta, the angle between these two vectors, is 90 degrees, that's 1. So in this particular case, the magnitude of that force, or I can just write it like F without a vector symbol, is equal to QVB. Since that's a centripetal force, that's got to be equal to mv squared over r, or m omega squared r. I got my velocity canceling out. Let's solve for r. So r would be equal to, that comes up, this goes down, so that's mv over qb. Recognize the power of what we have here. I create a magnetic field, and then I shoot charged particles into it. Now, how fast it's going, I might have some control over. It is possible to control how fast the particles are going. Magnetic field, I've created it, so I can create it to whatever strength I need. But I got these two variables here, which are dependent upon the particle. So if I shoot this particle into it, if I look to see that radius of curvature, what kind of circle does it start to make, I can now identify it by this mass to charge ratio, which narrows down the values considerably of what it possibly could be. I now have a method of determining subatomic particles based upon this ratio of mass to charge. So if I shoot, so let's say that I have magnetic field here. Those are all supposed to be dots, despite some get dragged out. I realize we're low on time. If you could have patience, thank you. Or if you need to go, I understand. If I shoot the electron into this field, all right, so got spin gun going there.
Spin gun. And then I got my, don't need my fingers going.
Would be the negative j hat direction?
Yeah.
All right, so
Yep.
V cross B is down,
Mackenzie just got stick.
but, and this is where you got to throw in one little extra bit there. This is pointing downwards. Q is negative,
Oh.
so it flips it.
Oh.
The electron will now be going this way.
I don't like that.
Now, sometimes what I'll do is the negative charge is going that way. I'll just pretend that's a positive charge going the other way, and then stick to the forced up. So if I shoot something that has a mass to charge ratio about that of an electron, I have a pretty good idea it's an electron. If I have some other particle which has a mass to charge ratio of an electron, except it curves this way, it's a positron.
That's right.
So I can now identify particles and their anti-particle equivalents. And I'll leave you with one last thought here before I hand back to tests. The force on the particle depends upon how fast it's going. So if I have a proton that's being shot into my magnetic field, as we talked about here, it's forced basically into a curve like this. As an observer, how fast it's going depends upon how fast I'm going. So if I'm just standing here in the lab frame, I can see the particle get shot by, I have some detectors, I can find distance divided by time, find the speed. If I'm traveling the same speed as the proton along with it, how fast is the proton moving relative to me?
0 meters per second.
Therefore, what would the force on the proton be relative to me?
0.
Right. So we are in this strange world here where the force depends upon the velocity, but the velocity depends upon the observer. And hopefully, it blows your mind just a little bit. But not as much as relativity will when we get to that. Any questions before I stop recording?
Could you finish the sentence, the force is always perpendicular to,
The velocity of the particle and the magnetic field.
oh,
Because cross products always produce something that's perpendicular to both vectors.
So we are still gonna be dealing with, protons and electrons in magnetic fields, even though there isn't necessarily like a positive and negative, it's just like north and south.
Yeah. And the trouble is, I've had some students who go into that plus minus mindset for magnetic fields,
Yeah.
and then they start blending in positive charges with positive magnetic charges, and they assume, oh, this is the north end, if that's positive, then my charged particle is gonna go away from it, and that's not the way it works. The force is gonna be perpendicular to the velocity, not parallel to it.
Okay, gotcha.
And it's possible you're not gonna make that mistake, but that's just, I've seen that happen too much. All right, I'm gonna stop.